Hey, welcome back. We are going through review problems for the final exam. So this is problem number 9 on the review slides. And the idea is that you have, let's see how I do on my 3D drawing. You have one mass that's going in a circle on a frictionless table, and then under the table is another hanging mass that's kind of providing the centripetal force for this guy. Terrible picture, but you can look at the slides for a better rendition. Okay, so we're told that M1 on the frictionless table, so this is M1 up here, M2 down here, and M1 rotates in a circle of radius r, and then we have M2 hanging below. So first, part A, so basically we don't have any numbers. Beautiful. It's just an algebra problem. That makes it easy. So really we're just given M1, M2, and R. Okay, so part A is draw a free body diagram for both masses and clearly label your coordinate axis for each object, which of course we would do. We always do that when we draw a free body diagram. Okay, so we'll do M1 first. Now M1 is the object going in a circle, so for this one, well, let's just think of the forces. I'm going to think of a side view, okay? So I'm going to be looking at it kind of from the plane of the table as it's over in this position. So it has the tension pulling it toward the center. I'll make it a little bit bigger. It has force of gravity. So I'm just going to put M1G so we don't confuse it with the other force of gravity. And then it has the force of the table pushing back up on it, the normal. So the coordinate axis that we should be using when we're doing circular motion, right, is this RZ T coordinate system. So R points toward the center of the circle, so that's our R direction. And then Z is kind of perpendicular in what we would normally think of as the Y direction. So that takes care of M1. M2, hanging under the table, is, we'll make its gravity a little bit bigger, like that. So M2G, and tension going back up. Okay, so this is the same string, same tension. Right? The tension doesn't change throughout the string. Okay, so then part B is analyze the forces on the hanging mass to determine the tension in the string. So that would be M2. So we're going to analyze the forces. So find tension, right? That's what we need to find. So we are going to, oh, I forgot my coordinate axis. Oh my goodness. Here's X, and here's Y. Phew. Okay, so M2 only has forces acting in the Y direction, so let's sum the forces in the Y direction to get MAY. Now, ideally, this mass is stays at rest, right? So when this is spinning at the right speed, at the right distance, this will stay at rest. So this is going to be 0. And from our free body diagram, in the Y direction we have tension, which is pointing in the plus Y direction, and the weight of the hanging mass, M2G, in the negative Y direction. So we have tension minus M2G equals 0. So that tells us our tension is M2G. Ta-da! Okay, and then C says find the speed that, so we're going to find V, that M1 must rotate in a circle of radius r if M2 is to remain hanging at rest. Well, we already said that that's what that tension is going to be for when it's at rest. Okay, so now we want to look at the forces acting on M1. So I'm going to sum the forces in the radial direction. That equals MAR. And remember, when the radial direction is always pointing toward the center, when something's moving in a circle, its radial acceleration is v squared over r. It is accelerating, right? Even if its velocity is constant, the direction of its velocity is changing, so it is accelerating. Okay, so that gives us that side. And then for the summing the forces, we have the tension. That's the only thing, right? So there has to be an unbalanced force, or a force directed toward the center of the circle for something to move in a circle. So we have tension, and let me put the M1 there, is M1. So this is the general relationship, right? For this problem, it told us that it was v squared over capital R. Okay, and then this is our unknown. We want to find the velocity. So I'm going to multiply both sides by R and divide by M1. Okay, so that will cancel out. And I'm going to just swap sides, so I get my unknown on the left, and I get v squared is tension times radius over m1. And then over here, I'm going to plug in the value for my tension. So it is m2g r over m1. This is v squared. And then I'm going to take the square root of that to get v by itself. So v is the square root of m2g r over m1. Very nice. So it's actually easier when you don't have values to plug in a way, right? Okay, and this is problem number 9 in the slides.